Hello everybody, welcome back again to electrical and electronic circuit analysis, where today we are going to talk about field effect transistor. Okay, two things we are going to describe. Let me say the principles of operation, the material, the different operation region within the characteristics, input characteristics, output characteristics. So we'll talk about field effect transistor, FET, and MOSFET characteristics, which is metal oxide semiconductor field effect transistor. Now, just to remind you, BGT, what we did, we control the base current. So a three-terminal device, collector, base, emitter, we control the base current to control the output current and voltage. Now, in MOSFET or in field effect transistor, we are not controlling, it's not current control device, it's a voltage control device. What we have here? We have here three terminal. We will call them to distinguish between them into drain, gate, and source. As you can see here, this is the source here, the drain here, and the gate here. One issue to be mentioned here is there is no electrical link between the gate, neither with the source nor with the drain. It means there is insulator between them. Okay, it's used in many applications, particularly in amplifier and logic gates. Logic gates, it's preferable to use FET rather than using BGT because of its characteristics. Now, MOSFET compared with BGT, it's work with low power definitely consumption, low voltage and power and current, and it's use less chip area and fewer process to manufacture in the factory. Okay, it's used in many applications for logic circuits or integrated circuits in memories and microprocessors. Okay, now here you can see this is the drain and this is the source and this is the gate. Between them, if you see this area, this is the insulator, oxide insulator, to insulate gate from the drain and source. So there is no electrical connection between them. Okay, we use N and P type as we discussed in diode and transistor, and the name of the gates are the name of the terminals are gate, source, and drain. And we have NMOS and PMOS. NMOS is the N-channel metal oxide semiconductor, and PMOS is the P-channel metal oxide semiconductor. The length we will talk about in this discussion here, this part. We'll talk about the length of the gate and how it affects the characteristics of the MOSFET. Now, the symbol for MOSFET, as you can see here, is just to remind you with the transistor. Okay, it was in this way. This is collector, this is base, this is emitter. Well, here we have a drain, we have gate, we have source. Sometimes they connect another terminal, which is body, and sometimes it's not there, to a fixed value, as example 0 to ground. Okay, so this is how it look like the MOSFET. Now here is the source, here is the gate connected to N type, here is example, and majority is P type, insulator here, and the gate connected to a terminal. So three terminal device, as I mentioned. Now there is a specific critical value of voltage which is called threshold voltage VT. Okay, it's specified. You can't find it in the specification for the transistor, for the MOSFET. Now this is important value we need to know, because based on the comparison between gate source voltage with the threshold voltage, we can know in which mode it's working. Okay, now when it is lower than the threshold, there is no flow of current, but when it becomes equal or greater than, then conduction layer of mobile electrons will occur, and like a field will happen for the current to follow through. Now, as I mentioned, we have similar to PNP in transistor, BGT and NPN. The same thing here, we have N and P. We have NMOS and PMOS. If I come to NMOS, you can see here specification VGS supposed to be greater than V threshold, so the transistor will conduct. And VGS greater than 0, it means it is positive. There is mode which is called depletion mode. We will talk about it in the next lecture, next session, which is VT lower than 0, it happened. Okay, now all this for NMOS. If we talk about PMOS, the opposite. I don't need to repeat because the opposite of this. Now, this is my transistor, my MOSFET. This is drain, this is source, this is gate. It's connected to the V drain source and this one to the V gate source. So similar to the BGT. BGT, the base connected to the VBB and the collector connected to VCC. Here the same thing, gate to VGS and drain to VDS. As you can see here, when we connect the voltage VGS to the gate here, current will not follow because it's open circuit. So I get always 0. You can see here, we increase the voltage in red, we increase the voltage, but always 0 current, because how it come, it follow through open circuit. It cannot follow. Okay. Okay. Now, cutoff region, you remember, just to remind you, in BGT we have 3 regions. We have cutoff region, we have saturation region, and we have active region. It's work in the active region as amplifier, as a variable resistance. Let's see how. I just remind you with BGT because I want to compare. Okay. Now, cutoff region, when VGS, okay, VGS lower than V threshold, okay, what happened? What happened is no current will follow. ID will be 0, drain current will be 0 when VGS lower than the V threshold, and the voltage, you see here, the voltage increase VDS, but no current follow between drain and source. Okay, it's not enough, good enough to make a conduction of current. Okay, now what happened if VGS become greater than V threshold? This is what we need to talk about, the characteristics here. Okay, have a look. Now VGS become greater than V threshold. What happened? Between source and drain, there is inversion layer occurred of electrons. It's like a field happened. For that we call it field effect transistor. It's work on the effect of the field which make this transistor work. It make a field of electrons layer called inversion layer. This field of electrons will be like a conduction between drain and source, control the flow of current from between drain and source. Let me show you. Okay, now if VGS greater than V threshold, now we are not anymore in the cutoff region, we are somewhere else. Now the second region, I will call it triad region. Triad region. When this happen, when VGS greater than 0, you see, and V drain source is lower than the difference between VGS and V threshold. This is called triad region. You see here the characteristics? See the characteristics. VDS, ID. I'm talking about here in the output characteristics. Now, when we increase VGS, what will happen to the resistance? I mean, the transistor as a resistance. It's reduced. When it is reduced, the current will increase. So you see the line increase. And up and up. You got it? Now this region is the region where we have transistor, the field effect transistor work as a variable resistance, as amplifier. While in BGT, it was working in the active region. Okay. Now current will follow between source and drain in this case. Okay. And as since VGS greater than V threshold and VGS minus V threshold is lower than, okay, or let me say VDS lower than VGD minus V threshold, the difference between them, then we have current to follow, and this is the triad region. I don't need to repeat for P channel because it's the opposite, exactly the opposite. As you can see here, this is NMOS when we have 3 terminal, B is there, and here NMOS when we have, here 4 terminal, here 3 terminal. The opposite here, you see circle, just to mention that this is P type, and the same thing, either 4 or 3 terminals. Okay. Now still in the triad region, you can see here VDS against ID in the output circuit. VGS, it was 1 volt. When it is increased, and decrease, we can see that the resistance reduced to the